last section of Chapter 7 here, 7-9, we're going to talk about the topic of differential equations. Now, differential equations, of course, there are whole courses taught about these, and so we're only going to look at a very, very tiny piece of this topic. A differential equation, first of all, is nothing more than an equation that contains a derivative. There are lots of types, but the only ones that we will look at will satisfy two conditions. They'll be first-order differential equations, meaning they only contain first derivatives. And secondly, they're separable differential equations, meaning that it is possible to separate the variables, get all of the x's on one side and all the y's on the other. All right. So let's take a look at a few separable differential equations. And in all of these, we're going to be finding what's called the general solution, meaning the plus c will be part of our solution. Later on, we'll talk about some situations in which we can get rid of that plus c, but for now, we'll look at these general solutions. When we finish, we're going to, if possible, solve for our dependent variable. So for example, here we're going to try and get an answer in the form y equals something. All right. Looking at my differential equation, I'm going to notice a couple of things. First of all, I'm going to define an x side and a y side. And the easiest way to do that is just to multiply the dx over to the right-hand side. And once I've done that, once I've got my differential separated, forever after, this is the y side and that's the x side. Okay. I need to get the y's out of the x side. And in order to do that, I'll start by factoring out the y. And then I can divide by it. And there we go. Our variables are separated. All of the y's are on the left, all of the x's are on the right. Once your variables are separated, you can integrate both sides. Of course, the integral of 1 over y dy would be the natural log of y plus c. And on the right-hand side, I would have 4/3 x cubed plus x, and again plus c. Now these are two different constants of integration, so maybe I'll label them C1 and C2. And then usually what we do is we imagine taking the C1 and subtracting it from the C2 to get a whole new constant over here on the right-hand side. I'm just going to call this one general C. Because this can be done in every single problem, typically I won't even bother writing the plus c over on the left. I'll just throw it on the right with the understanding that I've combined them. Sorry about that. Get rid of that ringing phone. Okay, so I've now done my integration, and the last step I would like to do here is to solve for that dependent variable. I'd like to get the y by itself. In order to do that, I'm just going to exponentiate both sides. So e to this power, and then e to this power. Over on the left, of course, e and ln are inverse functions, so that just gives me y. And over on the right, I'd like to do something, this is something that happens really, really commonly. I'm going to write this as e to the 4/3 x cubed plus x times e to the c. Multiplying means you add exponents, so this is really the same thing as I had up here. But then I'm going to notice that e to the c is just another new constant. So when I write my final answer, what I'll usually do is say, hey, this is like a constant multiplier now. So let me write this as capital C out here in front, times e to the 4/3 x cubed plus x. Now I know I often say, oh, don't worry too much about the little algebraic manipulations at the end like that. But this is an exception. This is something that happens so frequently and actually makes these equations much easier to work with when we start seeing what we can do with them, that this is worth getting used to and practicing each time you have this situation with a plus c up in the exponent. All right, there's my general solution. Still got the c in it. That's normal for a general solution. Let's try a couple more. All right, y prime is really dy dt in this case. Notice that the independent variable is t. And I'm going to write that right-hand side as e to the 3y times e to the negative t. I know I'm going to have to separate my variables, and I can't do that while they're both in the same exponent, so that'll help me as I move forward. I will multiply by the dt to bring it over to the right-hand side. And that makes this the y side, and that the t side. That means I'm going to keep the e to the minus t, and I might as well keep the 2 as well. And I want to divide by the e to the 3y. That needs to get moved over to the other side. So let's see, on the left-hand side now, I actually have e to the negative 3y dy equals 2 e to the negative t dt. And now that my y's are all on the left, my t's are all on the right, I can integrate both sides to solve my differential equation. So I'm going to do a couple of simple little u substitutions here mentally. Integral of e to the minus 3y is still e to the minus 3y, but the u substitution would have had the derivative negative 3. When I solve for the du, that would have become a negative 1/3 out in front. Not going to put the plus c on this side. Put it on the other side and assume I've combined them. All right, over here I've got 2. Integral of e to the minus t is e to the minus t. And again, the u substitution would have had a derivative of negative 1. Dividing that out, I would have divided by negative 1 here. And I will put my plus c on this side. All right, I've got the general solution, but implicitly I haven't solved for y yet, so let's go ahead and do that. I'm going to multiply through both sides of this equation by negative 3, just to clear the fraction there. So that's just going to make that a 1 e to the minus 3y equals, that'll be a positive 6 e to the minus t. And negative 3 times c is just another constant. So I'm just going to go ahead and continue to write plus c here, unless something happens that I really change the c, like taking the log of it or squaring it or something. I'm just going to go ahead and keep the c's plus c's. All right, I need to solve for y, so we need to take the natural log. Now notice that plus c does have to stay inside the natural log. I can't split it up or pull it out or anything like that. Logs don't work that way, right? Log of a sum cannot be simplified. That's going to give me negative 3y equals all of this. And so y would be negative 1/3 times this natural log. And there's my general equation, or general solution. All right, what about that plus c? How can I get rid of it? In order to get rid of a plus c, you need to have what's called an initial condition. In addition to the differential equation, you need some extra information. Oftentimes it tells you what happens when the independent variable is 0, but it can actually be anything. This could have been like y of 5 equals something. It doesn't matter. No matter what, we call it the initial condition. When that happens, I have values for, in this case, both x and y that I can plug into my general solution, and it allows me to solve for c. So let's go ahead and do this. I first need the general solution. Let's see here. If I multiply the dx over, I would have secant x times dy equals y cubed times dx. That needs to be the y side. That needs to be the x side. So I got to swap these guys. So I'd have dy divided by y cubed equals dx divided by secant x. And since I'm going to have to integrate, let's make these a little easier to integrate. Let's call that y to the negative third dy. And the reciprocal of secant would be cosine, so I can write that as cosine x on top. And now I'm in good shape to do my antiderivatives. Power rule, I have y to the negative 2 divided by negative 2. Going to put the c on the other side, equals sine x plus c. And let's see, I want to clear the fractions, so let's multiply by negative 2. Y to the negative 2, or 1 over y squared, equals negative 2 sine x, plus negative 2 times c is just another constant, so I'll continue to write plus c. And let's see here. If I take the reciprocal of both sides, I'd have y squared over 1 equals 1 over negative 2 sine x plus c. And so y would be plus or minus the square root of that. All right, that's my general solution. To get my particular solution, I'm going to plug in this initial condition. In this case, they're telling me that when x is 0, y is 3. So I'm going to put in 3 for the y. And since I did give a positive in that initial condition, I'm going to have to use the positive square root. Otherwise, it just won't work. Put in 0 for the x. And then we just solve for the c. I'm going to go ahead and square both sides here. So 9 equals, and that allows me to get rid of the square root, 1 over. Since sine 0 is 0, the only thing I really have in that denominator is c. Right? This is 0. All right, so 9 is 1 over c. C is 1/9. I now know the constant, and that means that my particular solution is y equals, and for this particular solution we had to take the positive square root, 1 over negative 2 sine x plus 1/9. All right. Although those initial conditions might seem like not such a big deal, in fact, they actually can very, very distinctly change the character of a solution. And so what I'd like to do next is take the same differential equation, we'll solve it for the general solution first, and then we'll put these 3 different initial conditions in, And we're actually going to graph the particular solutions that go with each initial condition. And I think what you're going to see here is the initial condition can actually make that general solution look very, very different depending on the value of those constants. So let's get the general solution first. I have dy dx equals y squared e to the minus x. I'm going to multiply the dx over to the right-hand side, which means the left is the y side now, and the right is the x side. So I'm going to keep the e to the minus x dx, and I'll divide out the y squared. So I have y to the negative 2 dy equals e to the negative x dx. My variables are now separated, and so I can integrate both sides. That's going to give me a minus y to the minus 1. I'm going to put the c on the right. And that's going to give me integral of e to the minus x is e to the minus x. But the little u substitution that I would have had to have done would have had a derivative of negative 1. Dividing by negative 1 is just going to throw a negative out there. And I'll put the plus c on this side. I'm going to go ahead and just multiply both sides by negative 1 just to get rid of those minuses. So I have y to the negative first, or 1 over y, equals a positive e to the minus x. And again, negative 1 times c is just another constant, so I'm just going to continue to write plus c. That's the reciprocal of y, so y would be the reciprocal of this. So there's my general solution. I'm now going to see what the c value would have to be for each of these three specific initial conditions. So for part A, I'm given x equals 0, y equals 3/4. Plugging that in, 3/4 equals 1 over e to the 0 plus c. 3/4 equals 1 over 1 plus c. I'm just going to cross multiply here. 3 plus 3c equals 4. So 3c would be 1, and c would be a third. That gives me the particular solution, y equals 1 over e to the minus x plus a third. Let's take a look at what that looks like graphically. And let's see, I don't think I need too big. Let's go negative 5 to 5 again. That's what I've got in there. That should be fine. The graph that I'm getting looks like it may be leveling off at about 3 rather. 1, 2, 3. So what I'm seeing here something that looks like this. For my particular solution. All right, let's do B. Y of 0 equals 1. So when x is 0, y is 1. Same basic process. I go back to my general solution, plug in y is 1, and x is 0. So I get 1 equals 1 over 1 plus c. If I multiply by the 1 plus c, 1 plus c equals 1. And so this time c is 0. That means I get y is equal to 1 over e to the minus x plus 0, which is just 1 over e to the minus x. I could now move that e to the minus x up, and I just get y equals e to the x. Whoops, sorry. I'll do that one more time. So plugged in a 0 here for c. Denominator is really then just e to the minus x, which I can then move to the top as an e to the positive x. So the graph of this solution is very different. That's just an e to the x graph, exponential growth, right? We don't even have to do that one. We know what that one looks like. So notice, with just a very slight change in initial conditions, we got two really different particular solutions. This one levels off near 3, and this one grows unboundedly forever. All right, we've got one more to do. Part C. The last initial condition was when x equals 0, y equals 2. So if I plug that in here, I get 2 equals 1 over 1 plus c. And again, I'm just going to multiply by the 1 plus c. So that'll be 2 plus 2c equals 1. So 2c is negative 1, and c is negative 1/2. So now my particular solution is y equals 1 over e to the minus x minus 1/2. All right, let's graph that one. Let's see here. Should be able to reuse this one. I'll make that a subtract 1/2. All right, once again, a very different looking solution. It looks as though this one's got a vertical asymptote, right? Hard to tell exactly where. We could do the analysis if we wanted to, but it's somewhere around 1-ish, maybe a little less. I'm not even going to label it because we didn't do the analysis to find out where it is. But the graph goes up to the left of the vertical asymptote and down to the right, like so. So we have three very different types of functions that are solutions to this differential equation depending on the initial conditions. If you go on and actually take differential equations, which you're actually qualified to do as soon as you're finished with this course, you will find that that's very typical, and you'll investigate this idea a bit more. All right, I'd like to finish this section, and in fact this chapter, by looking at one application of differential equations. Application to growth and decay. So, a very typical assumption to make is that a growth rate is proportional to the population. Right? Kind of makes sense, right? The more, let's just say you had a population of like rabbits or something, the more rabbits you have, the faster you're going to add additional rabbits and the population is going to grow more quickly. So we're going to assume in all of these problems that the growth rate is proportional to the population. The growth rate is really the rate of change of population. So I could write the growth rate as dp dt. Rate of change is always the derivative. And it's proportional to, so that's equal to some constant of proportionality k, times the population itself. So I'm going to start with this assumption in all of these, and then we'll add the details to solve the rest of the problem. In part A, we know that we have a population of 500 trout in a lake. The annual relative birth rate is 25%, and the relative death rate is 20%. Find an equation for the number of trout after t years, and graph it. Now, we've done problems quite similar to this, just with our knowledge of exponential functions, but I'd like to do this one as a differential equation and show you that we end up in the same place as where you would have expected based on what we did in a previous unit. So I'm going to use my equation right here, my growth rate dp dt is equal to, since the birth rate is 25% or 0.25, that would be positive, and the death rate would be negative, minus 0.20 times p. My k value in this case would be a net 5% gain in population, the difference between the birth rate and the death rate. All right, let's solve this as a separable differential equation. I'm going to go ahead and multiply the dt over to the right-hand side, and then I'm going to divide by the p. We will integrate both sides, and that's really the integral of 1 over p, so that would be the natural log of p. And this would just give me 0.05t. Plus a constant. Again, I'd like to solve for my dependent variable, so I want to solve for p. To get rid of the ln, I would have to exponentiate base e. Let those inverses get rid of each other, and now I've just got p equals, and we're going to do this again. I have e to the 0.05t, and then I could say multiplied by e to the c. Right? When you multiply, you actually add the powers, so it's the same thing. And then this e to the c is just e to a constant, is just a new constant. So I'm going to call that big C, multiplied by e to the 0.05t. All right, there's my general solution. I do have an initial condition. I was told that right now the population is 500 trout. So my initial condition, I'm going to say that at time 0 right now, p is 500. And plugging that in, I have 500 equals c e to the 0. That, of course, is 1. So c is 500. And so my specific particular solution is p equals 500 e to the 0.05t. Now notice that is completely consistent with what we studied when we were studying those relative growth rates for exponential functions. We had our starting value, and then we have our relative growth rate, right? We've seen it before. We now see where it came from. It actually came from the assumption that the growth rate is proportional to the size of the population. In this particular section, I'm going to ask that you solve differential equations to come up with your population equation or whatever equation you're trying to find. All right, let's just sketch this real quick. At time 0 here, we'd be at 500. And then we would just have an exponential growth function. It's kind of a slow growth function, just a 5%, but it would have to look like that, right? All right, I'm going to go back up and we're going to take a look at part B. Okay, we are now going to assume that due to fishing, there is an additional annual reduction of 15% of the fish population. Now I'd like to find an equation for the number of trout after T years and graph it. So, my rate of change is my rate of change from before, right? We already knew the 5% based on the birth and death rates. But we're additionally going to reduce by 15%, 0.15, of or times the population of fish. So this time dp dt is going to be a negative 0.1p. From there on, the solution process looks almost identical, so I'm going to run through it kind of quickly. dp would be negative 0.1p dt. I'm going to divide out the p and integrate both sides. So I get the natural log p equals negative 0.1t plus c. To solve for p, I will exponentiate both sides, giving me p equals, and I'm going to do the same little trick with the c. It's just going to bring the c down in front like it does here, times e to the negative 0.1t. Okay. Same basic equation, just a different constant, right? All right, once again, we're going to assume that we start with the same 500 trout. So I'm going to go ahead and say that at t equals 0, p equals 500. And unsurprisingly, we again get 500 for c. So my population equation this time is 500 e to the negative 0.1t. This time we've got a negative exponent, so this is going to be exponential decay. Starting with that same population of 500, it's just going to slowly decay down to 0. Over time. All right, the third one is a somewhat interesting one, and I'm just going to put this on a blank sheet of paper since I'm out of space. In part C, next we're going to suppose that everything up here is still true, but the DNR decides to stock the lake with an additional 200 fish per year. Notice this 200 fish has nothing to do with the current population. It's always 200 fish per year, not a percentage of the current population like our other growth rates were. We'd like to again find an equation for the number of trout after T years and graph that. So, my growth rate, dp dt, I'm going to steal from the last one, right? We knew at this point we had a growth rate, actually a negative growth rate, of negative 0.1p. But I'm now going to say, in addition, the growth rate is going to add 200 extra fish. So plus 200 fish per year. Not 200 times the population or anything, just plain 200 fish per year. This is a growth rate, so fish per year makes sense, consistent units. All right, I'd like to solve this. This one's a little bit different, so we'll take it a little slower here. I am going to go ahead and start by bringing the dt over to the right-hand side. And notice now this whole quantity multiplies dt, so I'm going to have to divide this whole thing over to the left. I'll make that a 1 over negative 0.1p plus 200 dp. And then all I have left on the right is dt. All right, I need to integrate both sides. And I know I haven't been writing it out, but this is just a little bit more complex, so I'm going to write out the u substitution for the left-hand side this time. let's let u equal negative 0.1p plus 200, the whole denominator. So du would be negative 0.1 dp. And if I divide by the negative 0.1, let's see, that would be negative 10 du, dividing by negative a tenth, right? Equals dp. So I'm going to replace this dp with a negative 10 du. So my integral becomes 1 over u, and again that dp, negative 10 du. The right-hand side's simple. Integral of 1 dt is just t, and we'll put our plus c over here. And then let's just go ahead and finish up this integral. That would be negative 10 times the natural log of u. I'll just go ahead and put the u back in there. And we've now got a form of our general solution. It's just not solved for p yet. So let's go ahead and solve for p. I would divide by negative 10, both sides. And negative a tenth t is negative 0.1 t. C divided by negative 10 is just a new constant, so I'm just going to leave that as plus d still. And I need to get rid of the ln, so let's exponentiate both sides. Negative 0.1p plus 200 equals, I'm going to do the same little trick with the c, c e to the negative 0.1t. Negative 0.1p would equal c e to the negative 0.1t minus 200. And now if I divide by negative 0.1, I am going to get p equals, again, c divided by negative 0.1, just a new constant, times e to the negative 0.1t. And negative 200 divided by negative 0.1 is positive 2,000. All right, we're almost there. Put in our initial condition. Remember that at time 0 we had started out with that population of 500 trout. So plugging that in, p is 500. That would be c e to the 0 plus 2,000. I'm going to subtract the 2,000 over. Negative 1,500 equals c times e to the 0, which is 1. And so my c this time is negative 1,500. So my particular solution, p equals negative 1,500 e to the negative 0.1 t plus 2,000. All right, let's see what that one looks like when we graph it. I can tell I'm going to get some fairly large values. I probably got to go up to at least 2,000 in my y-axis here. So in my window, let's go ahead and go from negative 5. I'm going to go out a ways. Let's go out 20 years. Scale of 1 is fine. And y, I'm going to go negative 500 to 2,500 with a scale of 100. I'm only interested in things beyond t equals 0, of course. And what I can see is it looks like this population is growing, but the growth continues to slow with time. In fact, if I went out a bit further, let's go out 50 years. Count by 5s. You can really see this level off. If I were to trace it, you can see that we are getting closer and closer to 2000. We're at 1967, 1975, and so on. That actually does have a horizontal asymptote at 2000. If you think about it, as t goes to infinity, e to the minus infinity would be 0 for that term. So our long-term or end behavior would be 2000 as t goes to infinity. So I'm just going to sketch that. We know we do start at 500. We'll level off at 2000. And the graph goes up more quickly at first and then begins to level off, like so. So once again, notice the very different behaviors of this population in these three circumstances, right? In the first one, we had a net positive growth rate, exponential growth. In the second one, we had a net negative growth rate, exponential decay. And in this last one, we had the outside influence of the DNR adding the 200 fish a year, which caused the population to continually increase, but not without bound. It's going to level off at a stable population of about 2,000 after a long time. This 2,000, usually we give it a name. 2,000 is called the steady state population. Population after a very long time levels off and stays steady at about 2,000. All right, that brings us to the end of 7.9.